All right, let's have a short prayer as we start. Heavenly Father, we thank you this morning for another opportunity to have this lecture. As we go through, pray that you guide us through, grant us the understanding that we need for this course. Thank you. In Jesus' name I pray. Amen.
Amen.
All right. So
Amen.
I discussed with you the other time when we met the content for the course, and I said that we're going to look at gears, and there are different types of gears that we'll be looking at. Majorly, we are going to look at spare gears, bevel gears, helical gears, and then the worm gears, then the failure of gears and lubrication of gears, hydrostatic torque transmission systems, performance and selection of hydrodynamic coupling and torque converters. Also, look at design of machines for production, computer-aided design, and then the product development, okay? And the assessment, I discussed with you that we're going to have attendance for 10 marks, then the assignment will be, we'll have one assignment and then one project, and each is 7.5, making 15. Then the quiz, we're going to have 2 quizzes, and that will be 15. Of course, the end of semester exams is 60, that will give you the 100% marks. Then we are now going to look at the introduction to gear design. Right, so we are starting with gear design first. So gears mainly are used for the transfer of power, for power transmission. Okay, so we want to transfer power from one source to the other. And when there is power to be transmitted or motion from one rotating shaft to the other, there are different alternatives that are there that could be used to achieve that. Okay, but there are some cases where certain machine elements are more feasible for such application. I get me. So we have power transmission devices like flat belts, we have V belts, tooth timing belts, we have chain drives, friction wheel drives, we have the gear drives. Okay, but in cases where we want slip-free, smooth, and uniform motion, and at high speeds, lightweight, precise timing, high efficiency, or compact design, in design criteria, the selection of an appropriate system of gears is appropriate in many cases or in all cases. Okay, and these gears will be able to fulfill the actual application where we want uniform motion, we don't want any slip, we want high speed, we want the system to be lightweight, and it should be precise in terms of timing, we want high efficiency. Gears are usually employed. We may also use belt drives and chain drives in cases where the cost, we want the cost to be very minimum or small, because chain drives and belt drives are less costly compared to gear drives. And but the limitation of it is that if we want to use chain drive for gear drives, in such cases, the spaces between the input and output shaft have to be wide. Okay, if there is wide space, then we can use it. But in cases where we have very tight space, small spaces, in such cases, we can employ the use of the gear drives. Selection of gears, types of gears and selections of gears. To select the best type of gears for a particular design scenario, it depends on many factors, and the factors include the geometric arrangement proposed for the machine. the velocity ratio required. That's the velocity ratio for that gear set, the type, the power to be transmitted, the speed of rotation, and then the efficiency that is needed for the system, noise levels and limitations. Some gears are noise, some are less noise. Some have less noise. Then cost constraint too is there. Some gears are expensive to manufacture and some are less expensive. So depending on the scenario, a typical gear set could be used. In general, there are three shafting arrangements by designers when contemplating the transmission of power or motion from one rotating shaft to the other. And each of the shaft arrangement would have different gear types or configurations. Okay. And the first one that we're looking at is the application in which the shaft axes are parallel. Where the shaft axes are parallel, that is, we have two shafts that want to transmit power from one of them, which is the input, and then the output. And the axes of the two are parallel. If they are parallel, there are types of gears that could be used. Then we have application in which shaft axes intersect. So in this case, we have the axis of the shaft intersecting at certain angle, right? It could be varying depending on the application, where we want to transfer the power from and to where we are sending the power. So in such cases where the axes are intersecting, we have different gear types and configuration that could be used. Then we have application in which shaft axes are neither parallel nor do they intersect. In such cases, the shafts are not intersecting and they're also not parallel. There are also different types of gears that are used in such cases. So we are going to look at each of these scenarios, each of these three scenarios, where the shafts are parallel, where they are intersecting, where they are not parallel, and they are also not intersecting. Okay, so let's look at this one. This is the first case where we have the application in which the shafts are parallel. If they are parallel, we could have external straight tooth spare gears, and we could also have the internal straight tooth spare gears. So spare gear, mainly the tooth are straight, okay, along the face of the gear. They are straight, and we have the in such cases the shafts are parallel. That is, the axis of the shafts are parallel. If you look at this configuration here that we are having here, let's look at this one for instance. Please, can you see my mouse pointer?
Yes, sir.
Yes,
Okay.
sir.
So
Yes, sir.
over here, you will see that the axis. We are looking at a view of the two gear set. We have the bottom one and then the top one. So we can see that this is the gear and that is the pinion. The pinion is actually the smaller gear. Okay, so over here you see this is the axis of the gear. That's the axis of the pinion. And if you look at it, you see that the axis of the gear is parallel to that of the pinion, and the gears are meshing at somewhere here. Okay, so in such cases, the axis of the output shaft and the input shaft are parallel, and you will see this view to where we have the axis of the pinion and that of the gear matching. All right, then the same thing can be said of the internal straight tooth spare gear. So here, in this case too, we have the axis of the gear to be parallel to that of the pinion. Then we also have external helical gears. Okay, we have helical gears, which is similar to spare gears, but in this case, the teeth are inclined at a certain angle to the axis of the gears. Okay, so here again, you will see that the axis of the gear and then that of the pinion are parallel, and the same thing we could see over here. All right. And one other thing that you should note here is this, the direction of rotation of each of the gear elements. If you look at the gear here, this one, you will see that as it rotates in the clockwise direction, if it's meshed with the pinion will be rotating in the anti-clockwise direction. You can see that. Then when you look at the internal gears too, internal gear like this arrangement that we have here, as the gear wheel is rotating the anti-clockwise direction, the pinion is also rotating the anti-clockwise direction. So you can see here that it depends on the application. It's in the case like this where you want, let's say, a smaller system or unit where you want the shaft to be rotating in the same direction, you could use this configuration to achieve that aim. Are we okay? Similar thing to the helical gears too, similar to the helical gears. Then we also have the double helical gears, which is also called the herringbone gears. The herringbone gears also are used in applications where we have parallel shaft arrangement, okay? And the herringbone gears is similar to, is helical, but here we have double helical, as we have helical gears at two sides of the gear wheel, two sides of the gear wheel. And the essence of this arrangement is that it helps to stabilize the system, to somehow cancel out axial forces. When we come to the design of helical gears, we'll get to know more about this. But actually, you see that as the helical gear, like the first arrangement, the C, the external helical gear, as the gears are rotating, there is transmission of power, but there will be the presence of axial forces or loading on the teeth due to the helix angle. All right, and that loading will tend to go towards one direction, and that will be exerting force on the bearings of the shaft. That will be axial forces on the bearing of the shaft, okay? But in cases where we don't want that, because that could cause, it could put more stress on the bearing. In cases where we don't want that, the presence of that axial loading on the bearing, it could bring another form of helical gear in the opposite direction or opposite arrangement to that at the other side. Okay, so if the teeth are designed such that we have angle to one side and another angle to the other side. So what happens is that the axial forces generated by one part here is cancelled by the axial forces generated by the other part. Are we okay? Are we following?
Yes, sir.
Good.
Yes, sir.
All right. So that is the one advantage of the herringbone gears. And if you have been to the mining companies, some of them use the herringbone gear, especially for their ball mills, mills that they use in grinding their ore material for processing. Some uses these herringbone gears. Then we also have the rack and pinion. So the straight tooth rack and pinion is also used in the cases where the shafts are parallel. And here, well, we see that the pinion at the rack, right? The rack, which is this particular one here. If you look at this one, it's actually something like a straight bar with a gear teeth on it. Well, that one is not run on the shaft, okay, but actually, natural sense, we know that that straight bar in natural sense could be like a arc of a circle which is having its center at infinity. So it will appear like somehow it's having an axis position at infinity. And the idea here is that the axis of that particular bar is in line or is parallel to the axis of the pinion or the gear. Okay, so in such cases too, we could use this parallel, we could call it the parallel shaft arrangement. Okay, then the next one, we have the applications where the shafts are intersecting. Okay, so when the shafts are intersecting shaft. Sorry, this is the intersecting shaft. Yeah. So this one should be before this one. So let's look at this first. When the shafts are intersecting, you see that we are going to have the shaft inclined at certain angle and they are intersecting. And the gear types that are usually used are the what you call the beveled gears. Okay, beveled gears, and they are mainly applied for such scenarios. So if you look at this one here, we call this one the straight tooth bevel gear, and the angle of inclination, this is the axis of the, say, the pinion, and that is the axis of the gear, and they are intersecting at a point somewhere here. If you look at it from the other direction too, you will see that the pinion axis and then that of the gear are also intersecting. All right, they're also intersecting at a point. All right, then we also have the zero bevel gear. The zero bevel gear, which is like this one here. Here is similar to the straight tooth bevel gear, but the zero bevel gear is such that the gear tooth or the teeth of the gear are inclined. Okay, they are somehow curved at certain angle or inclined at certain angle. Curved. It's similar to, we can say that this bevel gear, which is a straight tooth bevel gear, is similar to that of the spare gear, that is the straight to spare gear. And then the zero bevel gear is similar to that of the helical gear. Okay, so it's just a simple tooth bevel gear, but uh, the teeth of the gear are inclined at certain angle, all right, to the gear wheel. Then we also have this the spiral gear, bevel gear. So the spiral bevel gear, also the shafts of the, or the axis of the gears are intersecting, or the shaft on which they are transmitting, through which they are transmitting the power. Those two shafts are also intersecting, okay? And they are intersecting at a certain angle. And you see that the spiral bevel gear here, similar to the zero, but you see that the teeth on it is more of a spiral uh, in nature. Okay, so that is where it derived its name from. Then we also have the spare face gears. We have the spare face gears. In the spare face gears, you also can tell that there is a wheel, a gear wheel. Okay, it's just like a disc, a flat disc, and then we have the gears. All right, we have the gear teeth around it. So when you look at it, um, it is not, we will not call it, it's not inclined, it's not conical in shape. If you look at the bevel gears, the various of the bevel gears we've looked at, they are conical in shape, but this particular one is not conical in shape. It's just like a disc. And the other one, which is the pinion, is in the form of a spare gear. Sorry, it's in the form of a spare gear, and then the other one too is spare, but we have the gear teeth round the wheel of the gear. Then the shafts are intersecting at an angle, at a certain angle, but they are intersecting. That is what we need to note. Then it could also be a helical in shape. In such a case, we'll have the gear teeth inclined at a certain angle to the face of the gear. Then in such a case, it's not spare face, but it should be the helical face gears. All right. Then the other one is when the shafts are not intersecting, and then they are also not parallel. Okay, they are not intersecting, and then they are not parallel as well. In such cases, we have the hypoid gears, and that is like this one here. And this mostly you see these applications in the differential of automobiles like cars and those trucks. They use the hypoid gear arrangement, and you see that the axis of the pinion is different. It's not intersecting with the axis of the gear. All right. So if you look at this, for instance, if you look at it from the side view, it will appear like they are intersecting. Okay. But when you come to the other view of it, you will see that the axis of the pinion is offset from the axis of the gear. So that is that offset that we have over there. And we call that the hypoid gears. Then we also have the spheroid gears. So spheroid gears is also arranged in this form, right? In this form here, the gear it is in the form of a spiral, okay? And but you see the pinion. If you look at the pinion, it's more of a screw in shape. It's more of a screw in shape. It's conical, but you see that the cone angle is very, very small. And then if you also look at the gear itself, it's also it's not conical, okay? Though there may be some small cone, but it's very little. And the essence is to somehow increase the spiral angle. All right, so they all have different applications. And if you look at this one, you will see that the gear ratio for this particular one will be very high because you will have very many number of teeth on the gear. And when you come to the pinion, it's very, very little. So in cases where we want maybe a very high torque at a very slow speed, we could employ the use of this spheroid gears. And we also have the cross helical gears, which in that case, we have something like the helical gear, okay? They are crossed. The helical gears are crossing. And we have, if you look at it from one side, you have the helical gear, which is the pinion. If you look at the pinion and then the gear wheel, you realize that they are somehow overlapping. But if you look at it, or they are crossing each other. If you look at it from the other side, this is how it appears. And you realize that the axis of the gear itself is not intersecting with the axis of the pinion, okay? Then we also have the single enveloping or cylindrical worm gear. We have the worm gear, and then the next one is the double enveloping worm gear, which is this one here. All right. So these are the different categories of gears and then the different arrangement of gears, depending on the shaft arrangement and the various types of gears that we have. That's what we've discussed here. Do we have any question before we move to the next stage? Any question?
No questions.
Good. Okay. So let's go to the next slide. Then I'm going to look at certain terms that are used in gear design. Some terms that you may come across. If you look at this one, this gives us a section of a gear, a section of a gear, and there are different names depending on the area of the gears that we are looking at. Okay, so we have things like, we have things like addendum. We have the face width, addendum circle, top length, pitch surface element, working the pitch circle flank of the gear. We also have the tooth thickness, the space, the circular pitch, the root or the addendum circle. We have clearance or working depth circle. We have the clearance circle, sorry, the clearance, and then we have the total depth, and then other ones that we'll look at. But let's look at the various definitions of these terms that we are looking at over here. Then over here, we have something we call this showing a cross section of it, like and describing some of the terms that were not shown in the previous one. We have something like the pressure angle, right? Then we have the line of action, and we have what you call the pitch point. That's the pitch point over there, the base circle diameter, the clearance we've looked at the other side. Then we have what you call the common tangent, and then center to center distance, or the center distance, which is actually the distance between the center of one gear to the center of the other gear. And these are the gears that are meshing. Okay. All right. So let's look at what's the pitch circle. This is the imaginary circle, which by pure rolling action would give the same motion as the actual circle. So let's go and look at the pitch circle in this case. So over here, you see the pitch circle, this one, which is that dotted arc in the middle of the gear. And we could see the pitch circle. We could see the pitch circle here. All right, that is this circle, that one in the middle. Can we say it? And you will see that if we trace it, if the two gears are meshing, let's look at the pitch point. The pitch point is right here. The two gears are meshing. This is where the engagement is. You can see that point there. All right, so by pure rolling, assuming that these gears are not having teeth, then we have just two places. The one making the noise, mute your microphone.
To take him down, but not Lucky for Lovo, I'm not.
So that's it.
All right, so you see that if assuming that these gears have no teeth and they are just two circular discs, okay, let's say there are two rollers or discs, and one is having the diameter to be the pitch circle diameter, okay, with that diameter or radius. The other one too is having the same here, and those are forming two cylinders or two rollers. If they are to roll, the rolling action generated by this gear will be the same as though we are just having two circles of these parameters rolling against one another. Are we okay? So that is the pitch circle. That's the pitch circle. We have the pitch circle diameter, which of course is the diameter for the pitch circle. And we have the pitch point. It is the common point of contact between two pitch circles. So that's the pitch point. And I believe you identified that when I was showing us here. This the pitch point there. Then we also have the pitch surface, and it's the surface of rolling disc, which the meshing gears have replaced at the pitch circle. So that's the pitch surface. And if we go back, the pitch surface will be along this area here. Okay, see here we have the pitch surface element. That's the pitch surface element. Is along the mid section of the gear tooth. So the pitch surface is along that area. Then we also have the pressure angle, or the angle of obliquity. And it is the angle between the common number to two gear teeth at the point of contact and the common tangent at the pitch point. It is usually denoted by the angle phi. And the standard pressure angles that are mostly employed are the 14.5 degrees and then the 20 degrees. Okay, so if you come here, we can see the pressure angle here. All right, so this is the common normal. That is, if the two discs or the pitch circles of the gears are in contact, where they are in contact, if you draw a line through that such that the line is tangential to the pitch circle of one gear and tangential to the pitch circle of the other one. Okay, then if we have that line drawn, the angle between it and then the what you call the line of action is the pressure angle, and that line of action is the line that is normal to the surface. Okay, it's normal to the surface of the gear tooth at the pitch point. All right, and then that is where the force is, the normal force is transmitted from one gear tooth to the other one. Then we have the addendum, which is the radial distance of a tooth from the pitch circle to the top of the tooth. Then the addendum is the radial distance of a pitch circle from the pitch circle to the bottom of the tooth. And we can identify all that from this diagram here, that we have the addendum, which is this distance. This is what you call the addendum, the distance from this circle to that one. Okay, and then the top circle is the what we call the addendum circle, and then the bottom one, which is this one, is called the addendum. That is the addendum circle. Right, that is this particular one. Sorry, the addendum circle. That is this one here, right? The base one. Then the addendum circle is the one at the top, and then we have the distance between the pitch circle to the top, which is the addendum circle, is called the addendum. Then the distance between the pitch circle and then the addendum circle is called the addendum. Then we also have what the circular pitch, and it is the distance measured on the circumference of the pitch circle from a point of one tooth to the corresponding point on the next tooth, and it's usually noted by PC. So if we go back to this diagram, we can identify the circular pitch from here. Okay, that's a circular pitch. So the distance from this pitch point here, right, to the pitch point over here is called the circular pitch. Then we also have the all right, so mathematically we could say that the circular pitch is noted by this expression here. This expression says the circular pitch PC is equal to pi d on t, where the pi d is the pitch circle diameter, all right, and the t is the number of teeth on the gear wheel. For two gears to mesh together correctly, they must have the same circular pitch. That is what you should understand here. All right, note that for two gears to mesh correctly, the circular pitch for the two have to be the same. Okay, if D1 and D2 are the pitch circle diameters of the two meshing gears having the teeth T1 and T2 respectively, then for them to mesh correctly, say that the PC, which is pi D1 on T1, right, the pi times the diameter of the pitch circle diameter of gear 1 divided by the number of teeth on the gear 1 should be equal to the pi times the pitch circle diameter on gear 2 divided by the number of teeth on gear 2. And that means that D1 over D2 should be equal to T1 over T2. If we simplify this expression here, we say that for two gears to mesh correctly, D1, that is the diameter of gear 1, divided by the pitch circle diameter of gear 1 divided by the pitch circle diameter of gear 2 should be equal to the number of teeth on gear 1 divided by the number of teeth on gear 2. Okay. Then we also have the diameter pitch. It is the ratio of the number of teeth to the pitch circle diameter in millimeters, and it is denoted by PD. So mathematically, we can say that the diameter pitch is equal to T divided by the number of teeth on the gear divided by the pitch circle diameter of the gear, and that should be equal to pi on PC. Okay, because we know that PC is equal to pi d on T. So it means that if PD is equal to T on D, then means that we can say that PD should be equal to pi on PC. All right, you could derive that. Then the module, we also have what you call the module. It is the ratio of the pitch circle diameter in millimeters to the number of teeth. The ratio of the pitch circle diameter to the number of teeth. All right, and it is usually denoted by small m. That's the module. And mathematically, we have the expression m is equal to d on t. So the module is pitch circle diameter divided by the number of teeth on the gear wheel. All right, then we also have the clearance, and it is the radial distance from the top of the gear to the bottom of the tooth, and it is in a meshing gear. That is the clearance. So the radial distance from the top of the tooth to the bottom of the tooth is the clearance. The circle passing through the top of the meshing gear is known as the clearance circle. Let's go back and try to identify the clearance from this one here. So we have the clearance over here. That's the clearance. Okay. And what it's saying is that, for instance, if two gears are meshing, yes, let's look at this diagram here. If these two gears are meshing, you see that as one roll over the other one, there will be some small gap between the bottom of this gear, okay, and then the top of the other one. Can we see that small gap there? That gap is called the clearance. So the gears are designed such that the top of one gear will not directly rest on the crest or the bottom of the other one. So that small space that is created there is what we call the clearance. Then we have the total depth. It is the radial distance between the addendum and the addendum circle of the gear. It is equal to the sum of the addendum and the dedendum. It's equal to the sum of the addendum and the addendum. Then we also have working depth, and it is the radial distance from the addendum circle to the clearance circle, and it is equal to the sum of the addendum of the two meshing gears. Okay, so let's look at the working depth of the gear. Also from here, we can see that this is the working depth, which is the working depth circle is this one. The working depth should be from this point here. You can see this line up to that one. Okay, so when the gears are meshing, we said earlier that one tooth should not rest on the root or the bottom of the other one, and because of that, when the gears are meshed, there's some small gap in between the gear teeth of the other one, and then the root of this other one. So what happened is that small gap is called the clearance. From the end of that gap, that is from that point to the all right.
Adam, what I saw?
Please. Hey, you are making nice here. So from this point to the top of one teeth is what we call the working depth. So what we are saying is that the distance between the clearance circle, right, and then the addendum, that radial distance is the working depth of the gear. Then we have the tooth thickness, which of course is there. Then the width of the tooth measured along the pitch circle. That's the tooth thickness. So if you come back here again, we can identify the tooth thickness over here. So the width of the tooth, all right, measured from one pitch point to the other pitch point. So along the tooth circle, that gives you the tooth thickness. Then we have the tooth space, okay, and the tooth space is the width of the space between the two adjacent teeth measured along the pitch circle. So that's the tooth space, and that one too, you can see it here. That's the space of the tooth. All right, that is the tooth space, this area here, right here. Then we have total depth. Okay, I've not mentioned the total depth, and it is the radial distance between the addendum and the addendum circle of the gear. And it's equal to the sum of addendum and addendum. Okay, that's total depth, and working depth too is there. Then we have the backlash, and it is the difference between the tooth space and the tooth thickness as measured on the pitch circle. So the difference between the tooth space and the thickness as measured on the pitch circle. So if we take this diagram, for instance, if we take, sorry, I'm coming. Sorry, this is rather the face of the teeth, and the tooth space is talking about the gap from this point to that point, and the backlash is that distance between the teeth when, for instance, we have two gear teeth. For instance, if we look at this one here, this gear tooth, and then the space which is inside here, when this gear is meshing with this other one, with this one, when this is meshing with this other one, inside over there, you see that usually there is some small allowance that is given, okay, so that the fit between this gear and that gear will not be like it's forced fit. All right, it is to allow some free movement of one teeth over the other, or free rotation of one teeth over the other one. All right, so what happens is that that small free space, all right, which is allowed between the tooth, where we can say that the meshing tooth which is inserted in this area here, the thickness of that tooth should slightly be smaller than the tooth space, which is from this point to that point. So if the thickness is smaller than that one, then there'll be some small gap when one gear is meshing with the other. And that small gap is what we call the backlash for the gear. Then we also have the face of the tooth, which I've explained to you earlier. Then after that one, we have the top land, which is the top surface of each gear tooth. Then we also have the flank of the tooth. We have the flank, so let's go and look at this items here. So that is the top land, the face, and we have the flank over here. So the top side here is the face, and at the bottom we have the flank. Then the next one is the face width, okay? And that is mainly the width of the gear to measured parallel to the axis. We call that the face width, which we can say that is the width of the gear. Over here, the distance from this side to the other side. All right, so that is from here to that side is called the face width, which will generally be the width of the gear tooth. Okay, then we also have the profile. The profile is the curve formed by the face and flank of the tooth. The face and flank of the tooth forms the profile. Right, so there are different types of profiles. We have the straight tooth profile, then we have the involute profile of the tooth. The involute, we have the full involute, and then we have the stub involute profiles, okay? Then we also have the fillet radius, and it is the radius that connects the root circle to the root or to the profile of the tooth. Let's look at them. If you come to this diagram, the profile is actually this curved surface. So from the top here, move to the bottom is the profile, okay? And this particular diagram we are having is showing the involute profile. All right, then they have the fillet. That fillet, which is here, all right, that is at the root of the gear tooth. And the essence of that fillet inside there is to somehow relief, is to act at stress relief at the bottom during the operation of the gear. All right, and that is what we call the fillet radius. Then the path of contact, it is the path traced by the point of contact of two teeth from the beginning to the end of engagement. All right, so when the teeth are engaged and there is the two teeth are moving, right, the gear is rotating, the two gears are rotating, the teeth will be moving on each other. All right, so one will be moving on the other one. And then from the beginning of engagement, the end of engagement, and we trace that path, we call that the path of contact. That is the path through which the two teeth are in contact until they separate from each other. And then we also have the length of the path of contact. This is the length of the common number cut off by the addendum circle, the wheel and pinion. All right, then the arc of contact is also there. It is the path traced by the point on the pitch circle from the beginning to the end of engagement of a given pair of teeth. So when the teeth are engaged, we have the path traced from the pitch circle, which is actually we can measure from the pitch point. And as they roll over one another, by the time they disengage at a point, we trace that path and we have the arc of contact. And the arc of contact consists of two parts. We have the arc of approach, which is the portion of the path of contact from the beginning of engagement to the pitch point. And then we also have the arc of recess, which is the portion of the arc of contact from the pitch point to the end of engagement of the pair of teeth. And the ratio of the length of arc of contact to the circular pitch is known as the contact ratio. So we call that the contact ratio. And that is the number of pairs of teeth in contact at a given point. Okay. Let's look at gear failure. Before we continue with gear failure, I want to find out if we have any question. Any question?
No question.
No, sir.
You said?
No question, sir.
All right. Then the different modes of failure of gear teeth and there are possible remedies to avoid failure are what we are going to look at now. Gears may fail in bending. All right. May fail in pitting. We have scoring, abrasive wear, corrosive wear. But what we need to understand is that when gears are in contact, actually the tooth of a gear will be acting like a cantilever, okay? Like a cantilever, because you will see that one end of the gear is free, right? It's free, meaning that it's hanging. Let's look at this one here. You'll see that the gear is merged to the wheel. It's merged to the wheel, and then one end is hanging. All right. So what happens is if there is some force applied at the end of the gear, it will subject this gear element or tooth to bending, to subject it to bending. So one mode of failure could be bending failure, because it will try to bend the gear tooth, and at the end, it breaks off. When it breaks, it has failed. Okay. So we have bending failure, and we also have what we call pitting. It is the surface fatigue failure which occurs due to many repetitive head contact stresses. And a failure occurs when the surface contact stresses are higher than the endurance limit of the material used for the gear. Okay? And the failure starts with the formation of pits, which continues to grow, resulting in a rupture of the tooth surface. So there'll be some pitting or small chipping away of the surface of the gear tooth, and that will end up like rupturing a whole area on the tooth surface. In order to avoid pitting, the dynamic load between the gear tooth should be less than the wear strength of the gear tooth. And we'll look at that one. Okay. All right. And then also to avoid failure that is due to bending, the model and the face width of the gear is adjusted so that the beam strength is greater than the dynamic load. We'll look at those beam strength and dynamic load and what they are. We'll look at them in detail later on. All right, then we also have scoring. The excessive heat is generated when there is an excessive surface pressure, high speed, or supply of lubricant when they fail. All right, when supply of lubricant fail, or there is high speed, there's excessive pressure on the surface of a gear, to scoring may occur. And it is a stick-slip phenomenon in which alternative shearing and welding takes place rapidly at high spots. All right, so when the teeth are in contact, we know that there is high pressure at the surface of the gear teeth. All right, so as one moves on top of the other, that high pressure may create some welding at the points of contact because of high heat and pressure that will be generated.
I'll suggest you come like 6:30.
Hey. So this welding phenomenon, all right, when that is taking place, and then there's movement between the gear teeth, what happens is that it will try to be welding, and at the same time, then it will slip off. Okay, so it will be like it will stick to the teeth, will stick to each other, then they will share off. Right, so that welding and sharing, when that is taking place, and it's taking place rapidly as the gears are running, and that will cause scoring to occur on the surface of the gear tooth. Yeah. And this type of failure can be avoided by properly designing the parameters such as the speed, the pressure, and proper flow of the lubricant. If we have good lubricant and the lubrication is done well, we could avoid scoring, right? And that will help reduce the temperature at the rubbing surfaces within the gears that are meshing. And when that happens, we will be able to reduce the scoring or avoid it. Then we also have abrasive wear. When there are foreign particles in the lubricants, such as dirt, we may have some dust particles there. We may have certain, maybe some sand particles within the lubricating oil. They will be causing the abrasive wear, because as the gears are rotating and there is some foreign particle between the gear tooth, at the point where they are meshing, it will end up eating away the material on the surface of the gear tooth. Yeah. And this type of failure can be avoided by providing some filters that will filter the lubricating oil, or by using high viscosity lubricant oil, which will enable the formation of thicker oil film and hence permit easy passage of such particles without damaging the gear surface. Okay. Then we also have corrosive wear, and this corrosion may be caused due by the presence of corrosive elements such as additives present in the lubricating oils. There are times where there may be some additives in the lubricating oil, and this may cause corrosion of the gears. In order to avoid this type of wear, the proper anti-corrosive additives should be used. Any question? Any question?
No question.
All right, so we continue. All right, so in gear design, we have what we call the beam strength of the gear tooth. Okay, the beam strength of the gear tooth. And I would like us to end here, possibly, and we meet again, God willing, on when are we meeting? On Friday, eh? On Friday, when we meet, we'll continue with that, where we look at the various calculations that are used. So if you don't have any question, we will end here. Or do you have a question?
Yes, sir. So when are we getting how are we going to get the recorded version of the lecture?
I will post it on the VLE. I will send you the link. Eh? Okay.
Okay, sir.
All right, thank you. And your lecture material,
Sir,
I
think we do not have your enrollment key.
Don't worry, I'll set it up for you before we meet again.
Yes, sir.
All right, thank you.
So the slides and all that.
I'll give you the lecture material, so I'll print them for you. I'll give you the lecture material within the week. So, I'll print them for you.
All right, thank you, sir.
Thank you very much. Thank you for coming. God bless you. Enjoy your day. God bless you. Enjoy your day.